Inequalities. Now we'll have a couple videos on inequalities. So to start, I'll say, so far in algebra, we have focused a great deal on equations and on what has to be true to make things equal. And that's an important topic, but sometimes in math and even in real life, we need to find out whether something is bigger, smaller, or just not equal to something else. And this is the basis of the idea of inequalities. The test uses 5 inequality symbols that you need to know and understand. These are the 5 inequality symbols. So let's talk about these. First of all, the less than and greater than symbols. A is less than B, C is greater than D. First thing I'll say is that it might be helpful to remember these by thinking about that as, say, the jaws of something like a crocodile. In other words, it's open toward the bigger thing. The crocodile's hungry, so it wants to eat the bigger thing. That's a wonderful little trick that they teach little kids, but it can be very helpful actually if you have any confusion between these two symbols. Also notice that these first two have an inverse relationship. In other words, if A is less than B, that necessarily means that B is greater than A. So we can just swap the order around and reverse the direction in which the inequality is pointing. Now, the less than or greater than or equal to symbols. So A is less than or equal to B. C is greater than or equal to D. And so these are interesting because it leaves open the possibility that the two are equal or that one is bigger than the other. And again, these are also inverses. If A is less than or equal to B, that necessarily means that B is greater than or equal to A. And finally, A is unequal to B. So either one could be greater or less. All we know is that they don't have the same value. So all 5 of these are used in the specifications for problems. So at the beginning of a problem, it might say something like, if x is greater than or equal to 10, or x is unequal to 5, or blah, blah, and then they'll talk about the rest of the problem. So that is just a condition they specify to make the problem work. And so any of these 5 symbols can appear in that specification. Now, the first thing I'll say about these is, with inequalities, it is very important not to be naive about numbers. What do I mean by that, naive about numbers? Think about it this way. For example, the specification x is less than 5 does not mean the same thing as x is less than or equal to 4. And this is very typical. This is a very typical mistake pattern. And what's going on here, people are thinking that x can only be a number that they can count on their own fingers. So in other words, people are only thinking about positive integers. And so this is the type of confusion that arises when people get caught in that, when they're thinking about all numbers are just positive integers. All numbers are numbers I can count on my fingers. In fact, when you see the word number, or just when you see an x, and all it's talking about is an x, and they don't specify anything else, you have to think of all possible numbers. This could be positive, negative, or 0. It could be integers, fractions, and decimals. It can be any kind of number on the number line. The whole number line is open when we just have the word number or when we just see the variable x. Now think about this. Think of all the values that would satisfy the inequality x is less than 5, and that would not satisfy the inequality x is less than or equal to 4. Now, of course, there are no integers in that range, but there are many other numbers. So examples include all the decimals between 4 and 5. All of those are things that legitimately are less than 5, but they are not less than or equal to 4. And notice that last one in particular, 4 followed by a bunch of 9s after the decimal point. So that's a very interesting one. Of course, that number is less than 5, and you might think, well, gee, it's awfully close to 5, and yes, it is close to 5. Here's the mind-blowing part, though. How many numbers are greater than that last number, but still less than 5? And the answer, the mind-blowing answer, is infinity, between any 2 points on the number line, no matter how close those 2 points are, between those 2 points, there's an absolute infinity of numbers. And so that means if you leave out the numbers between 4 and 5, you're leaving out an infinity of numbers. You're leaving out more numbers than there are stars in the universe. So that is the magnitude of that error. So it's very important to be discerning when you read inequalities. It's very important not to fall into that trap at any point of thinking that all possible numbers are just the numbers that you can count on your fingers. You'll have to use the first 4 inequality symbols in problem solving. The test will not have you work with the unequal sign in problems. So when you actually have to do work for yourself, you could see greater than or less than or greater than or equal to or less than or equal to, but work that you have to do with yourself, you will not just see the unequal sign. The unequal sign might appear in the specification of problems. In that sense, you'll need to know it, but you will not have to work with it. An algebraic statement involving one of these 4 symbols is known as an inequality. All of these are inequalities. With equations, we can do almost anything to one side as long as we do the same thing to the other side and the 2 sides remain equal. Equations are very easy to handle that way. What operations can we perform to both sides of inequality that preserve the statement of the inequality? So in other words, we have an inequality, say greater than or less than, pointing in a certain direction. We want to do the same thing to both sides, and we want to understand, are those things still greater than or less than? We have to understand that. So, first of all, we can always add the same thing to both sides or subtract the same thing from both sides, and the inequality remains the same. So addition and subtraction work exactly the same way with inequalities as they work with equations. So that much is easy. So for example, if I have the inequality x plus 7 is greater than 2, and I want to get x by itself, I subtract 7 from both sides, and of course I get x is greater than negative 5. And so that is the solution range for x. Addition and subtraction work the same way with equations as they do with inequalities. With multiplication and division, things are a little trickier with inequalities. We can still multiply or divide both sides by any positive number. That will preserve the inequality. So if we know what we're multiplying by is a positive, if we're guaranteed of that, then multiplying and dividing with inequalities is exactly the same as equations. You can just do the same thing to both sides. What's trickier is that multiplication or division by a negative number reverses the order of the inequalities. So for example, if I have negative x is greater than 3, well, if I want to get x by itself, I have to multiply by negative 1. And of course, I'll multiply both sides by negative 1. But that has the effect of changing the direction in which the inequality points. So the negative x becomes a positive x, the 3 becomes a negative 3, and that greater than sign has to become a less than sign. And so the final statement is x is less than negative 3. One easy way to see why this is to think about what happens with ordinary numbers. So take the variables out entirely, and let's just think of ordinary numbers. So here are 2 valid, legitimate, true inequalities. It is true that 7 is greater than 3. It is true that 5 is greater than negative 2. Well, let's multiply everything by negative signs. It is also true that negative 3 is greater than negative 7. Negative 3 is to the right of negative 7 on the number line. And of course, negative 5 is less than positive 2. So in other words, in order to maintain true statements, when we multiply by negative 1, we have to reverse the direction of the inequality. So, here's a practice problem. Pause the video and then we'll talk about this. So we want to get x by itself, so much in the same way as with equations. First, we want to collect all the x's on one side, so I'm going to subtract 2x from both sides. Then I get 5x minus 2x is 3x. Now I'm going to subtract 7 from both sides. Now I'm going to divide by positive 3 because I'm dividing by a positive number. That's just like an equation. Everything else is just going to stay the same. I can just do the division on both sides, and I get x is less than -3. Now, sometimes they'll have the solution written in this algebraic form. Sometimes they'll write it on a number line. And of course, x is less than -3 is written on a number line like this. Notice there is a circle at the 3, an open circle, indicating that 3 is not a legitimate value. So -3 is not one of the values in this solution. -4, -5, -6, those are legitimate values. Those are things that are less than -3. But of course, -3 itself is not less than -3. So -3 is not included. So the endpoint is not included in that region. And the purple is the allowable region. Here's another practice problem. Pause the video and then we'll talk about this. Notice, first of all, that x cannot equal 0. If we made x equal 0, then we'd be dividing by 0, and we wouldn't have a sensible expression. Notice also that x has to be positive, because the fraction on the right is a positive number, and so the only way the fraction on the left is going to be greater than it, or equal to it, is if it's also positive. There's no way that it could be negative. No negative can be greater than a positive. So x absolutely has to be positive. Because all numbers are positive, we can simply cross-multiply. So just plain old cross-multiplying, we cross-multiply, and we get that 6 is greater than or equal to x. Well, if we combine all these conditions together, we see that x has to be greater than 0 and less than or equal to 6. And so this would be the allowable range. Notice that there is an open circle at 0 because that's not included, and there's a solid dot at 6. So the left endpoint is not included, the right endpoint is included in the solution range. Here's another practice problem. Pause the video and then we'll talk about this. This is tricky because this is a series of inequalities, but we do this exactly the same way as we do anything else. First of all, we can just subtract 5 from all 3 of them, and that's how we get -4 minus 5 is -9. We cancel the 5 in the middle, and then 17 minus 5 is 12. So we have subtracted 5. Now we're going to divide by -3 to get the x by itself. And of course, if we divide by a negative, it means both those inequality signs have to flip around. So they flip around like this, and that we get x is between. So x is greater than or equal to -4 and less than 3. So this is the solution range. And notice that we include -4. We have a solid dot there. We have an open circle at 3 because that's not included. So the left endpoint is included in the solution. The right endpoint is not included in the solution. And just to be clear, we could have any decimal up to 3. We could have 2.9, 2.99, 2.9999999. We could have any decimal as close as we want to 3, and that would still be in the solution. We just can't equal 3. In summary, we can add or subtract with inequalities exactly as you do with equations. We can multiply and divide inequalities by positive numbers. If we multiply or divide an inequality by a negative number, this reverses the direction of the inequality.